Hi, this is Owen Astrachan for Compsci 201, February 2nd, 2026. Part 2 of class after this WOTO. I hope that you've taken time to complete it. Here is a rebus. This one is tricky and convoluted, but I hope some of you will take time to figure it out now. There's the top row, the middle row, the bottom row, and we will go over it on Wednesday, but it's absolutely relevant to class and perhaps somewhat convoluted. Okay, we're going to look to review maps at the APT counterattack. And what happens is there's an array of strings. Each string is individual. And then there is a string of space-separated characters or strings. Since in this example, the strings are a single character long, but they might be many characters long. And you count how many times each character in the array occurs in the string. So in this example, A occurs 4 times, B occurs twice, and C occurs once. We create an int array to return, and we will look at 2 ways of solving this. One using collections.frequency, and we'll look at the big O for that. And then we'll look at maps, which will allow us to do things more efficiently. So let's solve APT counterattack in 2 ways. First, we'll take a look at the specification for counterattack. Although I've just gone over it, it's a good idea to look at it here, and I will copy the method name so we can see some examples. Here's 1, 2, 1, 2, 1, 2 Vorpal blade, and we can see that snicker occurs 0 times, so that's the 0 here. 1 occurs 3 times, blade occurs once, and runner occurs 0 times. So we'll go back and we'll be ready to choose that file, but I haven't done it yet. So I'll go to my IDE and I'll specify that we want to do counterattack Java, and I'll paste the method name, and we'll see that it's ready to go. I could test it. As I've said in the past, it's a good idea to write a public static void main. And I do that just to make sure that, well, I've spelled println wrong. I'm going to run this and verify that it actually works on my way to making sure that my code compiles. So it did work, and I'm ready to solve it. I need to count how many times each of these individual strings occur in this space-separated string. So I will be creating an int array to return that's the same size as the length of parameter words, and that's what I will return. And just as a reminder, in Java, when you create an array, as I've done here, it defaults to being filled with 0 or the equivalent. So the equivalent for an object would be null, and the equivalent for a Boolean would be false. Now what I need to do is separate this into its constituent string. So just as a reminder, str could look like this: A, B, A, B, A, B. And what we've seen before is calling .split on that makes life easier. So I will make a temporary variable that is the result of splitting all this first parameter. And now I have the individual components in here. And what I'd like to do is count how many times each string in words occurs in temp. So for each string here, I'm going to set ret, and here I can see I'd like an index, but here I've used a for each loop. So I'm going to change this to an indexing loop. And it's words.length, which is the same as ret.length. And I'm going to set this to, now what I'd like to do is collections.frequency, because I know that exists. But to do collections.frequency and count how many times words sub k occurs, I need a list here. And we can see that the parameter list, the variable list, doesn't exist. So I'm going to create it up here. And I recall that there's this handy method, arrays.asList, that will turn an array into a list. Now we can see that VS Code has automatically imported arrays and collections, but it didn't automatically import list. So either I can do that explicitly, and now my red thing goes away, my red underline, or I can do this abbreviation. There are different reasons to prefer both of those. So what did I do? I separated this into its component pieces by calling .split. I turned that into an array list or a list, because arrays.asList actually returns a list, something we'll see in P1. And then I used collections.frequency, which I knew existed. So I'm ready to test this, and let's see if I can find where it might be. It's in APTs. There's counterattack. I'll run it. And I got 10 out of 10. I'm doing my own green dance. Now, let's review that code to see what the big O is. This loop executes as many times as there are values in the words array. Let's call that n. So this executes n times. Now, collections.frequency executes, the call executes n times, but the complexity is as many values as there are in list. So list is the number of strings in here. 1, 2, 3, 4, 5, 6. We have two parameters, the number of values here, which I call that n, and the number of values in this string, I'll call that m, and try to be very precise when I speak. That means this takes order m time, because there are m values here, and it's executed n time. So this would be order n times m, and I'll make a little note where n, number of elements, number of strings in list, and m is number in words. Now, that's essentially quadratic, or a multiplicative factor of both n and m. And what I'd really like to do is use a map to avoid this collections.frequency call, which I'm doing over and over and over again. So what I will do is create the map, and I'm going to be counting how many times every character occurs. Sorry, every word occurs. So I'm making a new map, and what it's going to do is I'll make a little note here. Key, string, value, number of occurrences. So I'm still going to need to split this, because I'm going to need to see how many times this string occurs in this. So I'm going to be iterating over these and see, does it occur here, 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 here? So I will, for each of these words, I must count how many times it occurs here. And that number of occurrences is going to be part of my map. So to count how many times each of these occurs, I'm going to loop over these strings, which are in this list. So I'm doing this again. And what I will do is loop over each string in list. And I will count how many times it appears in my map by calling map.getOrDefault S0. So this map is the number of occurrences in this string of each individual character. And then I'm going to say map.put and I'm going to put the key, and the value is one more because now it's occurred one more time. So this is a standard kind of idiom that we've seen before. For each string, A, B, A, B, A, B, I'm looking up its value because the string is a key, and 0 is the default, and then into the map I put one more than that. So I've now counted how many times every one of these occurs. Now I'm ready to loop over the values in words. So I needed 2 loops here. One to count the number of string occurrences in list, and one to loop over what I'm doing here. I'm going to say ret sub k is map.get word sub k. Now I'm going to review this for a minute. And suppose words has A, B, C. Then A will have occurred 3 times, B will have occurred 3 times, and C will have occurred 0 times. When I call map.get on C, that's going to return null because C is not a key in the map. I could fail, but I'm going to actually replace this with getter default and say 0, so if it doesn't occur at all. Now, before I test this, let's look at the big O. This loop loops over every value in list. That's order n. This loop loops over every value in words. That's order m. So this is order n plus m, which is faster than n times m by a significant margin. Let's go back to testing this and see what happens. I got 10 out of 10 again. Voila. I'm very excited about that. And now it's time to continue class. We've done that. Here's basically a summary of what we did. And we could see that this was order n times m by calling collection.frequency multiple times. And here's what we did by looping over the strings and accessing them in a map. And then after we called getter default and we put it in the map, then we had to get the values out of the map. That's going to lead us to P1, which is due next week. And the ideas in P1 are related to machine learning, in that we're going to train a model, and then that model will be used to generate text based on what's in the model. In part 2, which will happen after next week, we'll try to use these same models to classify different authors. And the examples might be amusing here when we generate text. So we can see that a Markov model is not exactly what we're doing. This is what the AI overview explained. Generative pre-trained transformer models are far simpler Markov chain models. GPT models built on the same code of predicting the next word, their scale and complex architecture set them far apart from basic Markov chains. But they're related. It is a pre-trained model. It is generating text, but it's not a transformer model. There is an infinite monkey theorem that is part 1 of the assignment that you can get engagement points for. And there's a short story that you can read. I encourage you to look that up. There, you can find Markov chains in the wild. Make Donald tweet again. This is actually an operative example of a Markov chain. If you click on it, you will be able to generate random tweets based on having trained the model on President Trump's tweets. This is a way of combining children's books with Elon Musk's tweets, and that requires downloading and running it, but it's not simple to download and run. You need a x/Twitter key, but the first one works for everyone. We're gonna see 2 trade-offs in P1: a brute force model and a smarter model that uses a map. In the examples that I'm going to discuss here, we're using letters, but we'll think of words. It's easier in these examples to talk about letters. The concept is the same. My training model is the theater through that helps. And I'm going to generate text using a Markov model. we have to have an order on the model, and that's the number of words that are treated as a key, or in this case, the number of letters that are treated as a key. So I'm going to use a model 2 model, which means I'm using 2 letters together. And if I choose the 2 letters TH, then I need to find out what characters follow TH. And that's how I will generate random text. Here is that example in more detail. I have the theater through, that helps. There's TH occurring with an E following it. So I have this set of letters, this list of letters. E appears there. E appears there. Now I have R because it's THR, and then I have A. So the characters that follow TH are EERA. I get those and I choose one at random. So Markov processes have this random component. And in my example, I'm choosing E. If I choose E, that means the next key will be the H from the first key and this randomly chosen letter. So now I have HE as my key. And I can see that there's HE space, there's HEA, and there's HEL. Now I choose another character at random from those following characters, space, A, and L. That will give me a randomly chosen letter and a new bigram, a new 2-letter key, which is composed of the second letter from my original key, which was HE, and now this new one. I'm going to rescan the entire training text for each character example. Rescanning the entire text for TH means find the character that follows it, then look at the next occurrence of TH, find the character that follows it. So if there are n characters, I have to scan them all. That's order n. And then I choose a character randomly, as I've just discussed, and I use that as my randomly generated text, and I repeat and scan again. And that means to generate T random characters, I have to do this order n process of scanning the text T times. That's order T times n. And that works. And because the training texts are small, it's very fast. But what we'd like to do is use a map to make that more efficient. So what happens is we'll train a base Markov model by recording all the words. And we put them in an array list that's an instance variable. Then we'll choose a random k-word sequence. K is 2 in the example I just did. It might be 3, it might be 1. And that gives you a random context, which is a list of the k strings. In this example, I'm calling that W. I'm going to scan the entire text looking for W. I record all the following words and I choose one at random. And then I repeat with a new context. And I make a new context because I can't actually modify the list of strings. That's the original context. What we'll do then is, after using that idea of scanning everything, which we will call the simple Markov model, then we'll make a more efficient version called the hash Markov model. And these classes will share some state and behavior. They have the same training text, so they'll have some instance variables in common. They will have some different methods too. But we'd like to not copy and paste. We'd like to leverage concepts from object-oriented programming. And that's what we'll do in creating both simple Markov model and hash Markov model. Now, we've already seen examples of using toString, hash code, and equals, and we've made those more precise, for example, in Person 201. We inherit the default version from the class object. They're not very functional, so we have to make our own. In the example in P1, instead of using object as the base class, which every class extends, we will create our own base class to extend, and it will have both state and behavior. So we start with the base Markov model. You will be given that when you fork and clone the code. Then we will create a simple Markov model using that scanning text approach that I've just discussed, measure that, and then you'll create a hash Markov model, which is a more efficient version using a map. But they both extend base Markov models, so they share some code. And here we'll see some of what that code is in the public class base Markov model. We can see that there's a model size, a random number generator, and a sequence of words that's the training text. Now, these are listed as protected because that's how you ensure that they can be used in subclasses. Recall that private means they can only be accessed within the class in which they are declared, but protected means they can be accessed within that class and in subclasses. We also have a number to initialize the random number generator and a special string that the training text uses to indicate when the training text is over. So we have this base Markov model, and as mentioned, the instance variables are protected so that they can be accessed in the subclasses. There are some methods in base Markov that subclasses must implement. We will see in later examples that we could enforce that must by making the method abstract, but that's not part of P1. Instead, in P1, we have this method for getFollows, which is given a context, and you can see that there's a context parameter. It finds all the characters that follow that context in the training text. This default version just returns an empty list. That's not going to be so useful. And you'll see that when you originally run the chat 201 driver, as that's part of P1, and you'll get no text because you haven't yet implemented simple Markov model. So here is the code in base Markov that creates a random next string. And you can see that what it does is it calls this getFollows method with a context. Just as a reminder, here is getFollows. That's a method in base Markov. This random next string is a method in base Markov. But because of dynamic dispatch, when getFollows is called here on line 187, the version that's called will either be in the simple Markov model or the hash Markov model. And we'll see that it's order n in the simple model and order 1 in the hash Markov model. That's part of P1. Simple Markov, you scan the entire text for all occurrences. So if I have the big dog and the big cat have the big paws and I'm searching for the big, what'll happen is I find the big, that's dog. I find then I'm going to find and keep scanning, looking for, oh, I found the big again. That's now followed by cat. Now I'm going to scan, now I'm going to scan, now I'm going to scan, now I'm going to scan. Oh, I found the big again. I'm recording pause. I have to scan the entire text looking for the context at issue, which is the big, and when I find it, I record the word that follows it. So we can see, summarized on the bottom of this slide, I create this context, which is a list of strings, and then I test for equality in the my word sequence, which is the training text. Those examples show how simple works, and my word sequence, which is the training text, is part of base Markov, so I can use it in both simple and hash. That's order n, as I've already discussed. Find every occurrence of the context and find the following character. I have to look at all n characters to do that. I can't skip ahead because I don't know where each of these contexts, or 2-gram in the case of a model 2 Markov, is going to occur. So that's the order n. That means I'm looking at every one of the n characters. There's no expensive operation. I am actually testing the context to see if it's equal, but I'm assuming that the context size is small. So I'm going to ignore the time it takes to compare a context for equality within my training text. It won't matter unless these contexts are on the order of the size of the training text, which they won't be. Reminder that order n means linear. We don't care about the coefficients. And n squared means it's not linear, it's quadratic. How do we avoid rescanning? How do we make a smarter class, the hash Markov model? Well, I can scan the entire text once and store with each key, with each context, with each bigram in my example, the letters or words that follow it. So for TH, I record as the value in the map EERA. For HE as the key in the map, I record the values that follow it, space, A, and L. I do that once. That's in order n time I create the map. Now that does use storage because I have to store all these follow lists in the map. Then once I've done that, get follows just looks up a key in the map. And what will happen is the simple Markov model will be order n, and the hash Markov model will be constant time. You can test that by making a base Markov model. As you can see here, the variable on the left has type base Markov model, but it's pointing at or referencing a simple Markov model. That's because simple inherits from base. I could also make a hash Markov model, and when the code runs and random next string is called, the get follows method will be part of whatever model was created and what M points at. That's because of dynamic dispatch. So we can see here the get follows for hash Markov model and why it's order 1. We can see that we look up the context, which is a list of strings in the map. If it's not there, there is no follow. If it is there, we will return the value associated with the key in the map. That's constant time. How is this efficient? We create the map once. That's order n. And then to generate t random words, we do a constant time operation, t times. So what we get is, order n plus t, just as we saw with counterattack. That's much, much better than n times t. That brings us to Barbara Liskov, who won the Turing Award in 2008 for contributions to practical and theoretical foundations of programming language and system design, especially related to data abstraction. And the Liskov substitution principle is about object-oriented programming. What advice does she have for us? The advice I give people in general is that you should figure out what you like to do and what you can do well. And the two are not that dissimilar, because you don't typically like doing something if you don't do it well. So you should instead watch, be aware of what you're doing, and what the opportunities are, and step into what seems right and see where it takes you. Final WOTO. On the left, we can see our friend Markov and his own personal chain for a Markov chain. Please take time to complete this WOTO. Enjoy your day.